the video now. Start recording it right now. Yes, it's recording. So over to you, Jack.
Yep. So, hello everyone. It's my pleasure to join the ACNS short talk. The topic for today is charting the anharmonicity in inorganic mixed halide peroxides. And just to give you an overarching idea of this work, which was done last year, is that we are all familiar with phonons and especially dispersion relationship for solid state, and we can use inelastic neutron scattering to study in details the phonon property in a specific materials. Now, the problem in the recent era of computational material science is that we want to do high throughput screening of materials, so hundreds of thousands of materials. So while individual phonon spectra is understandable for individual materials, it's hard to cross compare different phonon dispersion relationship and to understand how one material's vibrational behavior change from material to material. So ideally, you will want to have some numerical measure to say how enharmonic is certain materials and how that affect the properties, so on and so forth. So this is the overarching idea of this work is can we develop some numerical measure for the enharmonicity of materials and how that correlate with their properties. Now, the materials we are working on is halide peroxides, and this has been quite a hit in the past 10 years. As you can see, this solar cell efficiency chart and the rise of halide peroxides is really steep during the past 10 years or so. If you look at the nowadays best efficiency is about 28% in the latest development. And for this blue curve, which is silicon based, it really went past for more than 30 years of development to get to that stage. So there's a lot of hype in these materials. And in particular, we are working on the inorganic peroxide solar cells. The reason why they are hot, all the materials has pros and cons. For example, this thing all first started as a hybrid material, the inorganic hybrid peroxides. The problem with that is that the material is sort of like a jelly, it's not very rigid like silicon sort of saying. That affect that long-term stability, especially if you have an organic molecule in there, you have UV degradation, and the materials might fall apart, right? But these materials are very easy to manipulate. As you can see in this picture here, you can change its compositions very easily by solution reactions. So start from one end of the spectra to cesium lead chloride to the other end of cesium lead iodide, which has a much desirable absorption band gap. You can easily tune the percentage of different halide compositions via solid state reactions. And as you can see here, it really gives you a broad spectrum of visible light that you can achieve the optoelectronic property for these materials. So rather than doing difficult vacuum doping technique like silicons, you can manipulate them in solutions, which is much cheaper. Now, the cons of these materials, as you can say, for example, the iodide, the cesium lead iodide, it has a suitable band gap of 1.73 electron volts for photovoltaic applications, but that's only for the cubic structure. However, at 300K, this qubit structure is not very stable and is transformable to tetrahedral phase with a reduced band gap. So even though you'll be able to synthesize a cubic phase materials, it might phase transform over time, and you no longer have the same thing when you put it into device. So that's something not so desirable from an application perspective. On the other hand, if you look at cesium lead bromide, it has a cubic phase that's stable at room temperature, but the band gap is not something more um, really desirable in this sense. So what people trying to do is use something called, compositional engineering, or if you prefer, just doping by changing the halogen composition, for example, to sort of manipulate the properties of halide peroxides. Now, in this recent work we did with Tom Wu in the School of Material Science Engineering is we try to look at the cases where the iodide and bromide are intermixed together as to form a solid solutions. Now, in the first stage, what we did is we thoroughly sampled the disordered structure of a crystal with iodide and bromide. So, when you mix two things together, they no longer form a perfect periodic cases, but the positions are disordered in space. So we'll be able to, with the use of high performance computing, to thoroughly sample more than nearly 500 different configurations of this disordered alloys of iodide and bromides at about 24 different compositions. And you can see this is the overall formation energy landscape, where towards the right-hand side, you have a bromide-rich composition, whereas in the left-hand side, you have iodide-rich composition. And as you can see from this computationally generated landscapes, the bromide-rich cubic phase is indeed more stable than the iodide-rich phase. And the stability, compared to the pure sample, for example, cesium lead bromide, the stability is much more enhanced compared to the room temperature. So that confirmed us that intermediate is a way to gain some extra stability in the materials. However, if you just do a DFT calculation at 0 kelvins, it means the dynamic stability of um, the material. And what happens is that if you shine the light on this material, there are the different halides will segregate, especially when you have more iodide in the sample, and when the light shines, the iodide and bromide will separate into two different domains. So you have an iodide-rich domain, bromide-rich domain. So you'll see as time goes by in this highly iodide-rich sample, two peaks develop when you keep shining light. And that's ultimately governed by the electron-phonon couplings in these materials. So if you look at generally, the cubic peroxides are known to be unstable structurally, and because it's in such a high symmetry phase, you try to lower your symmetry to gain some stability. And typically what happens is the cation might displace out of the center, or you have octahedral tilting, young Taylor distortion. Those are three common types that you're going to observe in peroxides. And there's a nice chemical review paper on these things to really talk about the electronic origins of the instability in cubic peroxides. And what you can see here is that if you look at the Banker energy of the cubic mix halide peroxides, the Banker energy change as you get more bromide, the Banker energy increase gradually. And if you take into account the thermal vibration of atoms, what you can do is you run a molecular dynamic simulation, and you get a snapshot along that simulation trajectory, which you can then calculate the Banker energy of each frame. And what you can see that is as the atom vibrate, the band gap energy increased quite substantially compared to the zero case, zero Kelvin case. So that's a manifestation of the electron phonon coupling in these materials. And surprisingly, what we found is that that upshift of band gap energy at finite temperature is almost compositional independent. Now, but that's just still a static picture of how the band gap energy change at 300 K. What happened is that because the um, atom vibrate and there's a strong electron phonon coupling, the phase relationship of the electronic wave function will be lost over time. And so that there's a dephasing term in this, how the band gap change over time. And if you analyze the data in more details, which we're not going to go through here, is you can find that for pure iodide and bromide, you can see that the dephasing time is much longer than any other composition with a mixed halides. So if you plot this full wave half maximum as a function of composition, you see here better that for pure halides, they have much longer band gap dephasing time, whereas for all the mixed halide system, the band gap dephasing time gets shorter. That means there's much strong electron phonon coupling the system where you have two different halide that sort of mix together. And that's probably why lots of these mixed halide exhibit this phase segregation problem. And we also want to look at the main things, look at how they affect the anharmonic vibration of atoms in peroxides. Phenomenologically, what people understand of the anharmonicity of halide is that if you look at the halogen atom that's in between two lead atom bound by the octahedral, the potential energy surface experienced by these halogen vibrations typically exhibit this double well potential. That's a manifestation of the vibrational anharmonicity in this material. And what you can do when you analyze the ND trajectory, or in particular the displacement of these halide atoms, you'll find that the blue curve is what has been sampled in the molecular dynamics simulation. If you fit the short, small amplitude vibration of these atoms, you get a nice Gaussian fit, which is what you would expect if the system behaved fully harmonically, right? Now, because you have this double well potential, you naturally see there's a high probability for this atom to vibrate with high amplitude. And what we can do is actually to measure mathematically the difference between this blue curve and this red curve as a measurement of anharmonicity. So the idea is that if the blue curve looks very different from the red curve, you will have something that's quite anharmonic. And this is what we did here to look at, how the anharmonicity of halogen vibration change as a function of um, as a function of composition. And for this material, somehow it's quite irregular. But the bottom curve is perhaps much easier to understand, as you can see that when the temperature rises from 100 Kelvin to 600 Kelvin, the discrepancy between these two curves generally decrease. That means the system becomes more harmonic as the temperature rises. And this is how people understand the temperature stabilization effect in halide peroxides. So that's how we saw this problem can be tackled in the first place when we have a hell lot of MD trajectory to analyze. But is there any better way to think about it? Because if you fit this blue curve to a Gaussian profile, there's always some uncertainty of within which range of this displacement you'll treat this thing as harmonic. The other thing is that, of course, atom vibrates three-dimensional space. You need to actually overlay weighting all the three-dimensional displacement all together. So earlier this year, there's another physical review material paper pop up, which is quite interesting. And they propose a new way to analyze the anharmonicity in the materials. And basically, the idea is that if the atom has been displaced by a certain amount in the ND trajectory, what you always can calculate is, first of all, what's the harmonic force constants in that materials under harmonic approximation. That's what we typically do in a standard phonon calculation. Right? To get the harmonic force constants, you get this harmonic curve. And you can also get the force from molecular dynamics simulation that truly reflect the anharmonicity of the materials. And if there's a discrepancy between these two forces, you have this anharmonic force experienced by atoms as they vibrate. Now it turns out you can't just use this FA. What you can do is to look at the whole distribution of FA across the whole ND trajectory you have sampled. And here is a comparison for silicon, which is very harmonic, with something that's quite anharmonic, the potassium calcium fluoride. You can see that for silicon, the standard deviation of this anharmonic force is much narrower compared to the anharmonic force distribution to these peroxide materials. And this standard deviation is basically what these people propose as a robust measurement of vibrational anharmonicity in the materials. And because the amount of forces depend on how much the atom moves, there's degree of structural distortion in the materials. And if we do some machine learning analysis, just cut a long story short, you can map out the differences between individual molecular dynamic frame into a two-dimensional space. And for example, here, each dot on this map shows a structure sample in molecular dynamic simulation. And to interpret this map, if two dots are close together, that means they are structurally very similar. But if two dots are very far apart, that means they are structurally very different things. And as you can see, if we color code each point with its anharmonicity score, you can see that some of this structure has very low anharmonicity score, where the other one has quite high anharmonicity score. That means, there's a certain correlation with how much the structure change when you vibrate and the corresponding vibrational anharmonicity. And what happens is that in another system where we look at how the anharmonicity change when you substitute lead by tin, because lead is a toxic element when you want to replace it by tin. The short story is that as you replace lead by tin, the band gap of all these materials decrease, and that enhances the coupling between the ground and excited state of the electrons, and that enhances the anharmonicity of the material. So tin halide peroxides typically are more anharmonic than lead halide peroxides. And this is how you normally understand if you think about double well potential. For all these halides, as you increase the amount of tin concentration, you start to see a much deeper well for the vibration of tin as they being distorted from their equilibrium position. And if you apply this to the molecular dynamic trajectory, here is 52 molecular dynamic simulation down for chloride, bromide, and iodide, each at two different temperatures, 100K and 300K. And you can see that the anharmonicity reflects some clear trend. First of all, as you have more team, the anharmonicity score goes up. That means the system behaves more enharmonically. Secondly, if you increase temperature from 100K to 300K, you can see that all the system be stabilized by temperature with a reduction in the anharmonicity score for all the compositions. And lastly, if you look at the truly stable phase, which is an orthorhombic phase of iodide, colored in red here, they have a very low anharmonicity score at 300K, so they are the stable structure at 300 Kelvin.
20 minutes.
Yep. So let me just sum up with my work. So over the past year, we really try to develop a tool suite to understand the electron phonon coupling in halide peroxides. So if you look at what people are interested in for halide peroxide as photovoltaic material that depend on their phase stabilities, depend on the electronic dynamic, and how it coupled with the structural dynamic. And all these things fundamentally are governed by the chemical bonding, how they bond together. And to really understand that, we have a tool suite of things we can do, from basic ab initio thermodynamic, whether they have a favorable formation energy, to the harmonic phonons. That's what typically probe in elastic neutron scattering experiment, and to further take into account the anharmonicity in the system, we need to run ab initio molecular dynamic at finite temperature, from which you extract the electronic information along the trajectory by running the band structure calculation. And put all this together, you can understand how the electron phonon couple together. And with a bit of physics-inspired machine learning, we can understand really what does this molecular dynamic simulation tells us. That has a more perspective to look at our data. And ultimately, what we are interested in is to understand this energy structure property relationship in those complex material, so that can guide future design to make these materials better. So for that, I conclude my talk, and thank you very much for your interest.
Well done. Very good. You've took 23 minutes. So that's pretty damn well. Sorry, excuse me. Pretty close to 25. So that's very good. I have to say, Jack, it's always surprising to see what people are working on. And for me, it's was a great surprise and a pleasurable surprise to see what you're doing. And actually, it's really interesting for me in particular, because we're doing very similar type of work and have done over the last few years. So there's a really strong overlap. It's very, very nice work. And I have to congratulate you on what you're doing. So I'm going to open up the floor to Jack. Questions? Don't be shy.
Yes, okay. First of all, Jack, that was a great talk. Since my first crystallography project 4.5 decades ago was on Anharmonicity. I was particularly interested in that aspect. But since the field has moved on a fair bit since then, if I ask a question about that, then I'll probably make a fool of myself. So I'll make a fool of myself on with another question. In fact, two questions. A first one, is how do you keep track of the work when you do 484 DFT calculations? That's a lot, and the bookkeeping must be fun.
Basically, we heavily rely on Python. So you basically, set up your Python script. Once that set up is literally just press enter and everything will just fire up on the HPC. So we don't really, do one by one with 400 of them. That's impossible. It's prone to mistake, and that's why we do a lot of programming to automate the whole process.
Okay, and that perhaps links into my second question. The computer modeling allows you to make very fine steps in a composition variation, but these very fine steps seem to show fairly sharp differences. Say for example, in the decoherence time versus X. If you could show that particular figure, and I'll point out what I mean. No, further back. No, further back. No. Yes, that one. Sorry, I've blanked it out a little bit here. So, yeah, the right-hand figure shows point by point variations that are fairly sizable. Now, are they real, or are that some sort of computational statistical error?
Okay. Let me put it this way. I think there's partially reflect what we observe experimentally, because if you look at here, the short decoherence times means there's there are stronger electron phonon coupling in the system. Whereas in the experiment, we show that as you have more iodide, they are prone to phase separation upon shining the light. So that's also shown that there are stronger electron phonon coupling in the system. So for us, we think that the experiment does, or the theory does reflect what's happening in the experiment. However, some people might argue with me because I show that universally when you mix two halides, the electron phonon coupling enhances, but with here at low doping concentration, we don't see a phase separation event. Now, there are other reasons. For what we understand, there might be a kinetic reason for that, because when you have very low doping concentration, the dopant has to move quite far away to come together with something similar. So that's why, perhaps why you don't observe these things when you have very dilute doping. So if I understand your question is that whether my simulation reflects something observed experimentally, I would say, yeah, partially they agree with each other to some extent. And if I may further elaborate with your question, is that of course we have like more than 400 structure being sampled, but in all honesty, all these MD calculations are done with the lowest energy structure of individual concentration, because that's what we are affordable to do. The caveat for that is if we can understand something that's more stable and they have this strong undesirable property, then perhaps it will reflect something that's slightly metastable in that composition. Right? There's a trade-off of how much we can do and how much knowledge we can really gain from this simulation.
Okay. Thank you.
Thanks, Gary. I just may I comment that this work. Let me just go and get the thing here. Annotate. So this work here, this is done for the 484 randomized structures, correct?
No, that's just, we have 484, but we have, from memory, is 24 composition, right? So along X, now 24 composition. For each composition, there will be a lowest energy one, right? So you just take the lowest energy structure and then you run the MV, electron structure calculation, to see how the electron phonon coupling change at that lowest energy structure. We didn't do that for all 480 structure. That would be computationally too costly.
I see.
Yeah.
So, but the randomized part of that 484 comes in where?
That's just when you, let's go back to here. So if you can see here, right, for example, in this composition at 0.4, that either is structure A and structure B, right? The A is the highest energy at that composition and B is the lowest energy at that composition, right?
Yep.
So there are all different compositions shown by these gray dots. But where we really look at the electron phonon coupling, we just take the structure that corresponding to the red dots, which we call it the leading edge, the most stable structure at each composition.
I see. I see.
Hello,
So
Anton.
Go ahead, Guochu.
Okay. Hi, Professor Yang. I have a question. Yes. So first of all, thank you very much for such a very, very nice, very good talk. Here, I just a question about this the figure on the right side.
Yep.
So as far as I know, and also I can see from this picture, and most of the time, if you dope a semiconductor, and normally you could, make the, for example, this absorbing peak a little bit broader or become broader and broader.
Yep.
And so my question is, when you're doping a pure system and then you get a broader peak, this can help the energy conversion in the solar cell, or it will. I mean, it's a good effect, or it's a negative effect. That's what I'm. I mean, I would like to know somehow, because I think I was thinking broader maybe make the absorbing how to say more photons transfers to to the transfer the electricity in the cell. But I'm not sure whether this is a correct guess or not. Could you explain a little bit about this?
I actually don't have a good answer. It really, now from my experience, it really depends on what's the mechanism that caused the broadening. Okay. From the experiment shown on the right, I didn't do it, so I can't comment too much detail because one of the students mentioned it. But back in my first ever PhD project, I do similar measurement on zinc oxide materials. Okay. Now for zinc oxide, as temperature goes up, there's a shift and broadening, right? But that broadening is very well known for electron phonon coupling because the excited electron hole pair coupled with the phonon and lose energy, right? To a first approximation, that's a scattering event, right? So if you think about photovoltaic application, those scattering is perhaps going to lose your photovoltaic efficiency, right? So there might not be something desirable. Of course, if you go down to lower temperature, your peak will be much more sharper, right? Because the phonon got quenched. You really need to look at how you understand that broadening of the peaks, right? In this case, like for example, if you go to a higher iodide concentration, the broadening might not just because of electron phonon coupling. That's literally the material phase segregate. There are two materials in there. It's not a pure solution, and that's something you might not want. Basically, your material changed over time. There's something you don't want. If you think about silicon, you don't gallium into silicon. No matter how much you shine the light, you think the gallium will still stay at the lattice site, but not whistling around. Right? That's how you interpret that data then.
Yeah, I was thinking because of course the temperature will strongly affect this like this peak, and also the how to say the a little bit about the band gap of the semiconductor. But however, most of the solar cells are designed to or expected to work during in the temperature range, maybe just around zeros to maybe 50 Celsius degrees C. So so I think this temperature range maybe is the most important range for a material for the solar energy conversion. So but I understand what you're saying. There's probably many different kind of mechanisms behind this to control. Thank you very much for your comment. Thank you.
Thanks, Richard.
Thank you. Bye-bye.
I think Richard's next.
Thanks, Anton. Hi, Jack. Great talk.
Hello,
I've got a really practical question.
Yeah.
If one was to try and verify these models using inelastic neutron scattering, what sort of experimental precision and resolution is required? Would you be able to differentiate between the different anharmonic models based on just GDOSs from powder samples? Or is this going to be a single crystal experiment that requires a lot greater detail and higher information content?
Well, I think it's quite tough. I suppose, this is something more I haven't done, which I probably need to look up, is that there are...
Well, first you need to know what the experimental resolution one can get, right? So it's about a milli EV, maybe a half a milli EV at best.
If you really need to resolve individual mode, I guess that would be quite difficult. If you just want the average, right, the best thing to look at is how these phonon dots evolve as a function of temperature, right? As we did together with titanium oxide. Now, the other thing to think about is that as temperature rises, the whole phonon band structure renormalize and the negative frequency disappears. So what you can do, I guess, is calculate a renormalized phonon density of state of phonon band structure and try to retrospect feedback to your experimental data. But at the end, if you really want to go down to say that peak at that MEV is belong to I guess you have to go to a high resolution.
Okay.
Yeah.
Thanks, Jack.
Typically, this happens with soft models, so they are occurring at low energy.
Okay.
Yeah.
Okay. Other questions for Jack?
Can I ask one?
Yep.
Yeah, sure.
So Jack is a very nice talk. It's really great. I just wonder, do you have any sample we can put a proposal in and can start do some measurement? Either Pelican or Taipan or Brimley filter, whatever
I was talking with Tom, and because he's mainly working on the experimental work on this side. He said he does have something quite interesting coming up, but he said let's keep it for the moment. But so if that does come up, I'll come back to you. There's definitely some sample coming up which he thinks is quite interesting.
That's good. I mean, you know what we can do, right?
Yeah.
So, yeah. If you have a real sample,
yeah.
and we can do the measurement and then can at least give some confirmation or test of your grid theory.
Yeah. Yeah. Definitely.
Okay, good.
Can I just say one thing, Daehong, is that we've already had several proposals and we've already run several experiments with these materials several years back.
I think recently I did have another PhD student across the corridor. I think he did some experiment with Richard and tried to come to me for some simulation. It's already at the back of the envelope.
Yeah, so I wonder, okay, related to this question.
Yeah.
Have you compared with any experiment data in your with your calculations?
So far for this set of system, the iodine bromine, no, not really.
Okay.
Yeah.
So that means there's no experiment data on the system you are investigating.
I wouldn't say that, Daehong.
Okay. Oh, okay. So just didn't. So at this stage, so that just okay.
Well, if you say phonons, but unless the neutron scattering, we haven't done that, but we have other experiments like PL, that sort of thing. We have comparison. Okay. Yeah.
I see. Okay, that's good. Yeah.
Thanks, Daehong.
Yeah.
Gary.
Thanks.
You said fairly early on in the talk that these weren't nanocrystalline samples. First of all, is there any difference between nanocrystalline and powder in terms of the calculations, or is that the nanocrystalline aspect simply a way of producing them for solar cell application?
Okay. The right answer for my simulation, I treat all the system as a bulk system. Experimentally, the original plan was to do it for a bulk material, which was I think that was how this paper was first published for bulk material. Then we will compare to thin film and nanocrystals. But the rate determines that, as you know, now is the pandemic. So I'm not quite sure the thin film and nanocrystal experiment are completed. But it will be interesting to know what's the size effect. Definitely, that's something interesting to know.
Thanks, Gary. Are there other questions? I have one last question, if you don't mind. So you show quite a plethora at the last slide. You show quite a plethora of different calculations. You know, sort of a circular. Next one, yeah, this one.
Yeah.
So each one of these circles represents a different type of calculation.
Yep.
I see. And so, and you linked, so it's actually getting the data out and putting into, and they're separate calculations. Isn't that correct?
Yeah.
Yeah. So there's, so actually there's quite a bit of work in getting data from one to the next, I would guess. You really have to understand the output, and then you have to put it into the input again, right?
Yeah, getting the output, getting the input, and then do the post analysis. But idea is that once you're done, once the follow-on work gets easier, right?
Yeah,
It's
sure.
always difficult to understand what to do in the first place.
Yes, indeed. So are these all running on the same machine, or are they on different machines?
Generally, we try to run it on the same machine, on the machine down in Canberra.
I see, the supercomputer there.
Yeah. This is a bit difficult, so we also need to offload some of the calculation to the local HPC at UNSW. But generally, it's not a big problem there.
I see. Well, that's very impressive, Jack. Thank you very much. If there are no more questions, I'd like to thank Jack once again. Thank you so much. It does require a lot of work to put together a really nice presentation. Obviously, you've done that. Thank you so much. Next week is going to be...
Thank you, Jack.
Thank you. Sam Yick. Sam is going to be speaking about SCO, which I guess is strontium cobalt oxide in thin film diffraction, neutron diffraction. Okay, everybody, until next week. See you. Thanks very much again, Jack.
Bye.
See you. Bye. Bye.